James. I'm one of the founders of M42. Delighted to be here. Big thanks to Jim, Fina and Andrew as always. Fantastic week. Before we get into the Q&A, a little recap, because it's been a long afternoon. BLANCA talked to us about digital twins and digital twins for drug discovery. Fantastic topic, something I think actually relevant for M42 and the Juvenescence partnership, which is very interesting. Lindsay's session was great. I was scribbling down some notes. I can't read all of my writing, but my net takeaway was that Rosalind is not the best, but really she is. I think Rosalind did pretty well.
Let's go with that, yeah.
And Monty Python probably had it right as well. That was good. DIPENDER, fantastic, was talking about lack of innovation, problems being time and money. Problems we all face, I'm sure, being time and money. But big impact on the drug discovery industry. 34 drugs per year for the FDA, which is nothing. 12 years from drug to a market, which is far too long. And $1.1 billion to bring a drug to market, which is appalling. Should be much quicker and much cheaper, and more drugs coming to market. TIAGO then talked to us about the EGP, their Emirati genome program, the largest PopGen program in the world. Some great strap lines, which I'm going to copy, which I haven't heard, but sequence once and use for life. He talked to us about the pharmacogenomics program, which is super exciting, premarital screening, and the newborn screening program, and more recently, the work around PopGen going clinical and PopGen to PopFam. So, without more of ado, I will turn over to questions.
Thank you. I have a question for TIAGO. Thank you for presenting a very impressive program. My question was, so you were talking about screening the entire population. That's obviously quite an ambitious aim. Is it a compulsory program for people in the UAE? And sort of how do you see that from an ethical perspective? And then secondly, more to do with like data governance side of things, like how is this data being stored? Is it going to be owned by the government? Is it going to be made available for sort of research? You say you're going to sequence and then use for life. How do you see that from a sort of data management ethics point of view?
So the EGP is volunteer, so people can go on, decide to go or not. So they have a withdrawal, and it's very similar, and it's very much based on GDPR, so it's kind of around those, if you know GDPR, that will be around those tactics. Now, I mean, this program, genetics, always raises a lot of ethical questions, right? So how do you call people? How do you bring people? How do you do genomics counseling? All that, of course, it's for the government to decide and to implement these public policies. So it's an ongoing effort. Right now, the genomic screening based on this is just at the bioinformatics side. So we are mapping all the variants, and of course we have new variants to discover because it's easier to queen-var and variants that are already kind of well established and high penetrance. And as always on this program, you start by the very high penetrance and very deleterious. Now, I think that this program will push the ethics because it's the first one that is at that scale, right? And so there will be a lot of new questions that are coming in between, of course, privacy, between issues where people really do not want to have this high rate of birth defects, and here is the sixth one. The government is very, very keen and is always very, I would say, it's very wary about respectability, about law, and so it's very, very always trying to go slow on many things. On the other hand, they have this program in their head, so I guess that they will start to see, okay, this is the people that you could actually do something with. How do you process that? I think it's going to be an interesting project. And this will push the ethic to legal in the world because it's the first one where all these problems are going to be faced there. So it's exciting and scary at some times.
Great, thank you, TIAGO. I was going to ask you about the public health initiatives through M42. As you know, in the UK, we have Our Future Health, which is going to collect longitudinal data population-wide. We've got 2 million signed up already. genetic and also epigenetic information potentially. Are you going to be following through your population, the data you've collected already throughout time over the next X years? For example, the Dunedin study in New Zealand, they've got 50 years of data.
Yeah.
They've got a good amount of epigenetics as well.
So currently, this is one program, right? On one shot, so to speak. Now there is one, so the UAE population for the insurance, which is paid by the government, can cost people every 3 years, and there is maybe an opportunity to do longitudinal from from the fact that people need to get that insurance. But currently the program is not set up. I mean, as a bioinformatician, longitudinal data is what makes this powerful more than anything else, right? So the idea that you get longitudinal is what really would make this even go to another level. Also, the electronic health records has longitudinal data in the sense that you have all the visits, so you can do, which we are doing. We can do like a flashcard where you can have all the visits and put this in electronic content. I'm sorry, I forgot to tell you that the government has a program or is thinking about making this available to researchers, and so I think that will come even in the context of researchers, also startups, the genomic oasis, but it's not yet fully established. But the government has said very clearly they want this data set to be available to everyone.
What is the story behind the name? Why it's M42? The story behind the name.
So the story behind name is that it is, so it's actually a merge of two companies. One is Mobile Health, the other was Group 42. 42 is the hitchhiker that's the galaxy. And it's also, I think M42 is also an Orient star, that is the North Star, and so it kind of has all these symbolic of idea that we want to be ambitious, we want to look for the patients, the innovation for healthcare and so on, but it's a mix of all these ideas that come together. Yeah.
So I've got a question particularly targeted at LINDSAY. Sorry. You're looking at SNPs close to genes, but you're looking essentially in one dimension, and yet genes in the nucleus are three-dimensional. Have you tried to incorporate 3C or high-C data into your reasoning? Horrible question, it increases the complexity enormously.
No, it's a good question. So although we do look in one dimension, I think the model implicitly learns something about folding, because it has to, otherwise it will always pick the nearest gene. So somehow it understands some relationship between the sequence and the probability that that variant is acting over a long range. High-C, I think again, I'm getting slightly off my kind of areas on which I feel comfortable, but the resolution is quite poor. So I think for something like this, it wouldn't be great, but I do think the model implicitly learns something about the way that the DNA folds in 3D. It's a really good question.
And then I have one follow-up, sorry, for DIPENDER. And that's really the hypothesis, well, I suppose this goes to the particle genetic analysis, the hypothesis that there is one target for a particular indication and therefore one drug for that, and yet with aging, it's a well, I'm taking the words out of Ellen Roll's mouth here, but it's a complex emergent system, and perhaps we need to be drugging nodes within a complex system and restoring homeostasis to the system rather than just completely ablating a specific target. So how do we do that? How do we actually take that extra step to improve Rosalind, to do all these other things, but take into account systems drugging rather than one target, one drug, traditional drug discovery?
It's a fantastic question and probably can't be covered adequately in the next few minutes. The aging is a complicated process, as is coronary artery disease, as is rheumatoid arthritis, as are most chronic acute diseases. There can be some targets that are efficacious, there are combinations that are efficacious. In the case of optimizing the impact, minimizing the adverse effect profile and the overall benefit for the patient. If we take obesity as a paradigm, GLP-1 analogs are clearly efficacious. Are they likely to be the only effective drug for obesity? No. Are they likely to be the best ever drug for obesity? No. Are they likely to be used alone or in combination? We've already seen from tirzepatide, probably in combination. That certainly works well. We've got amycretin coming in as well with amylin analogs. So the question is, what is the optimized therapy for any given indication, chronic disease or otherwise? and how does that vary across different time points and different population subgroups. So there's a lot to consider. It's multi-dimensional. There isn't going to be a one-size-fits-all. There's going to be a combination, and that's without even getting into the realm of multi-morbidity and the commercial landscape. That is why this is such a complicated field. The point is that appropriate use of human genetics can maximize our probabilities of being successful. It can minimize cost and it can improve efficiency. That doesn't mean it's going to solve all our problems.
We've got time for one more question.
This is a question mostly directed at Dr. Gill and Dr. Edwards, because I think Professor Rodriguez, this is going to be kind of, you've already answered this in the talk. It's about the development of filters for genetic analysis. Basically, I'm asking, when you're looking for explainability in your models, or trying to follow through the rationale of why you think that genetic analysis is important, how much do you focus on using things like filters based off mechanistic models to kind of perform that deterministic kind of step?
Sure. Especially when you're talking that this pump works. I'm ready. Thank you.
You took it.
No, I know.
It's a really good question. So I see myself as a glorified man. Right? So we have very clever statisticians, machine learning people like LINDSAY, and they do all this wonderful work. Deep dive analysis, they spend years, PhD after PhD, and they say, look, this is how we understand statistics, this is the genetics, and this is what the variant is doing. And I come in as a clinician, and I say, okay, I understand a bit of genetics, and I understand what it's like to be a sick patient, what it's like to treat a sick patient, and what it's like to work in developing drugs. How do we integrate all of that? If the model is spitting out something that to me seems like gobbledygook, I'll say, I don't believe you, right? We're not going to do this. So it is a case of having implicit filters. Now there's various other proper ways of doing that. You have positive controls. Is it recreating what we already know? Are there orthogonal models that make distinct assumptions? Are there different forms of evidence? How does it triangulate with epidemiological approaches, with some of Bianca's work with animal studies? All of that goes into it. There is never going to be one experiment that is going to answer all our questions. It's always a case of optimizing, triangulating, and minimizing assumptions, and then taking forward what is most likely to maximize efficiency.
So proud of myself. I'm not absolutely sure I completely understand the question, but I think you're talking about kind of how much do we believe a model if we don't know how it's making a prediction, like the trade-off. But is that not what you're asking? Because I don't quite know what we
What I'm kind of asking is, if you're building, say, a neural network,
Yep.
and you've got a data set,
and you've got what, sorry?
You've got a data set.
Yep.
And you might run that through some filters. You might say, I don't think this particular type of variance is got anything to do with the thing I'm trying to train. So I'll remove that from the data set. And then I will try to purify my predictions based on that. And there's lots of different ways you can do that. I was wondering how much you do that, because that's part of model explainability.
We don't do that. I mean, what I would say is machine learning models are generally determined by three things. The inductive biases baked into the model. So kind of how am I going to trick my hypothesis based on my models broadly trainable with finite data, the data you put in, and then your loss function. So I guess I would only do that. Like if you do that, you've got a model that predicts on the data you put in. I mean, yeah. So I'm not 100% still not 100% sure I understand, but maybe we can catch up afterwards.
Now we realise that some people have to go, so we don't need to make them feel really uncomfortable, but we did say a 4 o'clock finish. And actually, I also said that I wasn't going to say anything at the end, but what I am going to say is a huge thank you. Come on. Unfortunately, already left, so she won't hear our clapping, but Laura and Trish together really put the groundwork into this. And I also want to thank Martin, Dr. from Juve Labs, for doing an enormous job in helping design the programme, bring in speakers, actually really think intellectually about the shape of the Science Summit. And then obviously, thanks go to Jim for supporting all of the work that we do here and for establishing the Longevity Forum and particularly the Science Summit and supporting the work in my lab more widely. So thank you to everybody and thank you to all our wonderful speakers who have done an